You're listening to the Effective Statistician podcast, a weekly podcast with Alexander Schacht and Benjamin Pieske, designed to help you reach your potential, lead great science, and serve patients without becoming overwhelmed by work. So today it's a really scientific topic, causal inference. And I have the world probably most renowned researcher in this area here, Miguel Hernan. So stay tuned. This is a really, really great episode. I learned about Miguel Hernan maybe something like 15 years ago, where he was publishing about marginal structure models and how you can use them to better understand causal inference for HIV treatment and things like that. And at the time, I found it fascinating how you can not only adjust for baseline covariates, but also for time-varying covariates in observational research. So now talking to himself is really an honor for me. And so stay tuned for this outstanding interview with Miguel Hernan. By the way, talking about outstanding scientific content, there's a lot of really great stuff coming up in June in Gothenburg at the PSI conference. So if you want to have a lot of really, really great content packed in 3 days, then see you there in June in Gothenburg in Sweden. And you will probably suffer from having too many choices. Yeah. So usually when you go to a conference, you see, maybe there's this one talk in the morning here and this other talk in the afternoon there that you want to go to. Well, at the PSI conference, you very often want to kind of clone yourself so that you can be in different sessions at the same time. You know, like in Harry Potter, Hermine does. So this is how great the content is. So see you there. Learn more about this conference at psiweb.org. Welcome to another episode of the Effective Statistician. And today I'm really pleased to talk with Miguel Hernan. Hi, how are you doing?
Hi, how are you, Alex? I'm fine. Thank you for having me here.
Yeah, and it's actually quite easy to make this interview as he's currently not in Boston, but in Madrid, and that allows for a much easier time zone to have this interview in. But before we get into the main topic of the interview about causal inferences, maybe you can explain a little bit where you were coming from and how you got interested in causal inferences.
Well, I'm a physician by training. And when I was in medical school, something that fascinated me is to learn how you have to treat patients. I always wonder, how do they know that? When they tell me, for this type of patient, you have to give this particular treatment. My question was always, how do they know that? And that was really the beginning of it. It turned out to be a question that is very hard to answer, and I'm still trying to figure it out.
Okay. And couple of your earlier research was in HIV. Did you specifically work in this area?
Yes, I am doing a lot of work on HIV with my colleagues. It is an area that, well, first, it was very important. I trained as a doctor at a time when the internal medicine wards of the hospitals were full of people with HIV. It was a problem that I witnessed from very, very close. And on top of that, it turns out that it is an area in which the treatments are given over time. So these are time-varying treatments. And not only the treatments are given over time, but also, of course, the confounders change over time, time-varying confounders. So it was the ideal setting for a lot of the causal inference methods that I was working on with Jamie Robbins in the mid-90s. So that became a very important part of my own research.
Yeah. And I think it's also an area where there were becoming more and more treatments available. And it was pretty impossible to run head-to-head comparisons against, all treatments against each other, and understanding what works best in all these different scenarios. And so I think there was much faster observational study coming available than lots of the clinical trials. Also at the time, network meta-analysis wasn't really a thing. That was coming much later in the research. And if at the time we would have been possible to do these network meta-analysis things and much more kind of indirect comparisons, would you have gone in the same direction at the time?
Who knows? That is a counterfactual question. There are some type of things that you can do with network meta-analysis, some things that you cannot do. Some of the questions that we were asking were questions about the effect of treatment strategies that are sustained over time. And that means you need to adjust for non-adherence to that treatment strategy. When things like let's start antiretroviral therapy the first time that the CD4 count goes below 500. And that means that a network meta-analysis of something like that would be very hard to do even today, because you have to work with the groups as they were defined in randomized trials, and there is typically not the possibility of adjusting for adherence. So for some questions, you would still need to use observational data with rich information on time-varying confounders.
Yeah, that's a really good point that, network meta-analysis are not the answer to everything, especially given that usually for them, you don't have access to the patient level data. You need to rely on, literature data. You can only do, what's published in terms of the summary statistics. You can't, recompute any things like that. You very, very rarely have any information about post-randomization time-varying covariance. So that is nearly impossible to have. But let's start, before we get into the more difficult things, let's start quite easy. So if we have a study that has only an observational study, that has only 2 arms, and of course, like in usual observational studies, these have differences in the baseline variables. What is the best way to adjust for these differences so that you can compare more like to like?
There are many levels to that question. One is that, of course, it doesn't matter whether it is an observational study or a randomized trial. You have an imbalance in baseline risk factors in both types of designs. You will need to adjust. But we expect that to happen in an observational study much more often than in a randomized trial. Then about how to adjust for those imbalances in risk factors. The short answer is that any method works, really. You have enough data and you can do whatever you like best. For some people, it will be propensity score matching. For some people, it will be inverse probability weighting. For others, putting the variables as covariates in the model for the outcome. G estimation is standardization. Really, any method will work in that simple case. And it becomes a matter of personal taste, simply, in many, many cases. But the really important part, I think, for causal inference from observational data, we have, as you said, 2 groups, 2 treatments, or 2 treatment strategies that we want to compare. I don't think the most difficult part is the method that we need to choose to adjust for the confounders. The most difficult part is defining the 2 groups. And that is what a lot of problems with observational studies are. If you go in the past where people were comparing current users of some treatment with never users, right? So that was the real problem. The problem was not so much adjustment for confounding. You could adjust for baseline imbalances beautifully, and the study would still be biased because we were comparing current users, permanent users, people who have already been selected after having used the treatment for some time with people who were not using it. Everybody knows now that we shouldn't do that, and now we use new user designs or things like that in which we compare people who start treatment and people who don't. But that's only the first step. There are many questions for which it's not really a new user versus a non-user, is someone who is starting a treatment strategy versus someone who is not starting a treatment strategy. And by starting a treatment strategy, it may be starting a new treatment, or it can be stopping a new treatment, or it can be switching to a different treatment, or a million other things. So it's really a comparison that needs to resemble what we would do in a randomized trial. That's in our analysis of problems with observational studies in the last couple of decades. It has been really hard to find examples in which the problem was bad adjustment for baseline confounders. It is much more common to find studies that are horribly biased because they were not defining the groups and the start of follow-up, the time zero of follow-up at the right time.
Yeah, I think if you have observational data that comes, for example, from a claims database or from any kind of other database that is updated on a regular basis, then understanding what is exactly the index date that you're speaking about, what is the kind of start date for each of the patients, is not a trivial topic. It becomes much more easier if you have something like a prospective observational studies that you're implementing, where you make the inclusion criteria in such a way that, you know, all the patients start a new treatment at baseline. All the patients start or switch a treatment at baseline. Then you have a much more kind of clear index date. But in real life, we usually don't have that. So yeah, that is a very, very good point. In terms of selecting the groups, it's this treatment algorithm is a really interesting thing. I'm just thinking about when, you know, there's a new guideline coming out or these kind of things, you want to compare, for example, what's happening before or after the guideline. And then maybe things are more easy to define. But where typically the problems in others, you know, in defining the groups in these observational settings?
Typically, at least in many cases, the problem is in how to do in the observational study, in the observational analysis, what is very natural and easy to do in a randomized trial, which is making sure that the start of follow-up, the time zero, is the time when an individual meets the eligibility criteria and also is assigned to a treatment strategy. And this is obviously done in randomized trials when we start the follow-up at the time of randomization, because the person is eligible at that time, and also that's the time when the person is assigned to a particular treatment strategy. So in trials, it's very simple. But the fact that it's so simple makes it hard to see that is a fundamental principle of a study design. And any study that doesn't respect that basic principle is at a very high risk of bias. In observational studies, therefore, we, as a rule or by default, there may be exceptions in some cases, and we can talk about those, but by default, we should try to make sure that the start of follow-up for every individual is the time when the person meets the eligibility criteria and the person is assigned to a treatment strategy. And this is, in our experience, this is the most difficult part for a lot of people. Sometimes it's because, as you were saying before, if we are comparing starting a treatment versus not starting a treatment, or having a vaccination versus not having a vaccination, we can define the time zero for those who start the treatment, for those who are vaccinated at the time of the vaccination, at the time of the treatment. But what do we do for those who are not receiving it? When is their time zero? And there are simple ways of dealing with that. There are ways like just choosing a random time zero. That is exactly what we do in a randomized trial. Really, we are choosing a random time in the life of a person that happens to be close to us when we are recruiting for the trial. So we could do that and choose just a random time zero, or we could match the time zero of those who are not treated with those who are treated. There are multiple ways in which that could be done. It's not always done right, but there's no reason not to do it right. But then a more complicated aspect of this is when what we want to compare is a treatment strategy that involves something that you have to do over time. And let me give you a very, very simple case. When we say, okay, I want to know whether taking aspirin for 3 years is better than taking aspirin for 1 year, for some outcome, any outcome that you like. Okay, now at time zero, in a randomized trial, people would be assigned to 3 years of aspirin or 1 year of aspirin, and we will know who is assigned to each group. Very easy. But in an observational database, we see people who start aspirin at time zero when they are eligible, but we don't know who is going to take it for 3 years and who is going to take it for 1 year. So if we do the naive thing that I'm sure everyone in listening to this knows is not the right thing to do. If we do the naive thing of looking at people who take aspirin for 3 years and compare them with people who take aspirin for 1 year, that is a recipe for immortal time bias. And that's a reason why there's a lot of studies that are biased in the literature. So that's something that we cannot do. And this applies to any strategy that is sustained over time. So we cannot look into the future for time zero to decide who is in each group. Without looking into the future, some investigators are lost because they don't know how to classify people if they don't know what they are going to be doing. Again, there are ways of doing this that are correct and that never use information that we don't have at time zero at baseline to classify people into one group or the other. Exactly the same as we never use information from the future in a randomized trial to classify people at baseline. So once these techniques are more widespread and people use them in a more standard way, like things like the G formula or things like cloning and censoring and weighting, there are methods that can be used. Then we will have eliminated what can be the most important problem in observational analysis now, which is this mishandling of time zero. And once we do that, now we can start talking about whether the risk factors are not balanced between one treatment strategy and the other. But that conversation, we can only have it after we have fixed the other problem, because there is no way we are going to adjust our way out of the bias that we can have, the selection bias and the immortal time bias that we can have when time zero is not in the right place.
Okay, yeah. So once we have adjusted for these biases, between the two treatment groups, we can only adjust for all the variables that we have observed, not for those that we haven't observed or haven't observed correctly enough. How do you kind of communicate how robust the analysis are against any kind of variables, any other bias that you couldn't adjust for?
That is a fundamental problem, of course, of observational analysis. That's why other things being equal, we would prefer a randomized trial to an observational study. We could do both in the same population with the same treatment strategies, the same follow-up, the same outcomes. If everything were the same, and the same person would prefer study with randomization at baseline. So what we do in observational studies is we can think hard about what are the reasons why the people in each treatment arm are different on average, and measure them and adjust for them carefully. That's really the best that we can do. After that, there is no way of proving that we have succeeded. But there are some indirect ways of building confidence on what we have done. One of them is the use of negative controls. And let me just give you an example. I was mentioning the vaccination before, right? So earlier this year, we were doing the first real world evaluation of the COVID vaccines in Israel. And we had to compare people who had been vaccinated and people who had not been vaccinated and see what the effectiveness was. We had that information from the randomized trial, from the phase 3 trial that Pfizer did. This was the Pfizer BioNTech vaccine, but that trial was relatively small, and we didn't have very precise estimates for the more serious outcomes or by age group or for pregnant women or that were not even included in the trial. So we were doing this with real data from electronic medical records from Israel. And after we designed our analysis in such a way that there were no problems with time zero and all these other things that I mentioned before, because that is the first part. After that, the problem was, well, are the vaccinated and the unvaccinated, are they comparable in terms of their risk of COVID-19? Because we suspect that they're not. That people who choose to be vaccinated soon have a different behavior and have a different way of interacting with others. Maybe they're using masks more often. Maybe they're being more careful in gatherings, etc. And that makes a direct comparison of the vaccinated and the unvaccinated very dangerous. So, in fact, when we compare vaccinated and unvaccinated people, we found that the vaccinated, without any adjustments except for age and sex, we found that the vaccinated had a lower risk of COVID. But they had a lower risk of COVID 1 day after the vaccination, 2 days after the vaccination. For the first week after the vaccination, or 10 days, they had a lower risk of COVID. And that was impossible. That couldn't be an effect of the vaccine, because we know from the phase 3 trial that doesn't happen, that there is a period during which the vaccine has no effect, maybe between 7 and 12 days. So by combining information that we had before the observational analysis was done, we could conclude that there was confounding, that the vaccinated were different from the unvaccinated and they could not be compared. But that is very helpful, because then it means that we have one way of, quotes, testing whether there is confounding. And then we started to adjust for more and more things. And we realized that there were very subtle differences between these two groups that had to do not only with their with the population group that they were in, but even with the neighborhood in which they live. Because some people in some neighborhoods were more likely to get vaccinated or less likely, and also that was associated with the incidence of COVID in that part of the country. So we had to adjust very, very finely by matching on place of residence and many other variables. And after doing that, we saw that in the first 10 days, there were no differences between the vaccinated and the unvaccinated. Then after that, you start to see the differences that are increasing, and the vaccinated had a lower risk of COVID. But it cannot be because they're different from the unvaccinated, because if they had been different, we would have seen those differences in the first 10 days. That is an example in which we can use something that we know about how the world works, about how the vaccine work to design our observational analysis in a way that gives us confidence that confounding cannot be explaining the whole thing. And now we can proceed and generate inferences for things that we would not get from the randomized trial because it wasn't large enough.
Yeah. And I really love this example with vaccination, because it also shows that treatment outcomes and the selection can depend on many, many other things other than kind of the typical biological things that you would measure in clinical databases, like pre-treatment, symptoms, disease state, all these kind of other things. But it can depend on your personal risk profile, on your behavior, on your profession, of all kind of different things, or in this case, your neighborhood. And having this kind of understanding of how the data is happening is really important. So digging deeper into the background of the data is immensely helpful here. So we have just talked about kind of what we do if we have two treatments. How does that, differ if we get into multiple treatments? So, for example, if you do propensity scoring, you look for the probability of getting one treatment versus the other. And very often a logistic regression is used for that or similar kind of tools. How would you do it if you have multiple treatments? How do you come up with a good propensity then?
When there are multiple groups, we have people assigned to multiple treatment strategies. See, that doesn't happen very often in randomized trials because it's hard to do a trial with many arms. But that's really one of the advantages of observational studies, that we can do that almost for the same price. So it's a very important setting. Let me just give you an example. I was talking before about HIV. And in HIV, you might want to know, I mean, this is now known, but I'm talking about the early 2000s or 2010. People wanted to know when to start treatment, when was the best time to start antiretroviral therapy. And eventually, there were a few trials, but they had only two arms. You start at level when your C4 count first drops below 500 or when it drops below 350. But with the observational studies, we could look at 30 arms. We could look at essentially every level of C4 count between 600 and 200 in steps of 10. And that means that is an advantage if we can adjust for confounding in the right way. So when we have multiple arms and the treatment strategies are sustained over time, again, when we are talking about things that are sustained over time, we cannot use some adjustment methods. For example, we couldn't use propensity score matching because our method is designed to match at baseline the treated and the untreated. But now we are talking about a treatment that keeps happening over time. And at each time, we need to decide whether the person is following the treatment strategy or is not. We couldn't adjust for confounding by putting the variables, the potential confounders in the model for the outcome because the confounders are changing over time. I mean, we put post-baseline variables in the model for the outcome, we can get bias. We cannot use instrumental variables, even if we had an instrument, because the conventional instrumental variable estimator doesn't incorporate time-varying treatments. There, essentially, we cannot use any conventional method, but we can use what is known as the G methods. So the G methods are essentially, there are three types: the G formula, inverse probability weighting, and G estimation. These are methods that Jamie Robbins and others have developed since the 1980s. These are methods that are designed to deal with time-varying treatments and therefore allow us to compare treatment strategies even when there are multiple treatment strategies over time. And that is really the way to go. In practice, the most commonly used G methods are either the G formula or even more frequently inverse probability weighting, which is the easiest one to use. But as soon as we have sustained strategies over time, whether we have two or we have multiple, the only option that we have left in general is the use of G methods, and all the other more conventional ways of adjusting for confounding, like propensity score matching or putting the covariates in the model for the outcome, like in a Cox model, or any of these classical ways of confounding adjustment cannot generally be used for sustained treatment strategies.
Okay. If for these G methods, if you are a statistician and you want to explain how these works to a physician, how would you do that?
That is a very good question. I've been trying to do that for many years. I don't think I've always succeeded. The easiest one to explain is inverse probability weighting, which is actually, in the simple case, is the same as epidemiologic standardization. But here, what you explain to people is that, look, if you have information on the confounders, then you can give different weights to different people in your study population with the goal of making sure that after you give these weights, mathematically, you eliminate the association between the confounder and the treatment. So there is an association between the confounder and the treatment, which is why there is confounding, plus an association between the confounder and the outcome. Okay, you don't touch the association between the confounder and the outcome, but you give weights to people in such a way that the association between the confounder and the treatment mathematically disappears. And as soon as you do that, there is no confounding. So the weights themselves are eliminating the confounding. The advantage of using this method is that you never have to condition on the confounders like all the other methods do. You use propensity score matching, you are conditioning on the propensity score, which is a function of the confounders. You put the confounders in the model for the outcome, you are conditioning on those confounders in the model. And it is that conditioning what creates bias when we have time-varying treatments and time-varying confounders, and there is a feedback between them. By weighting, we never condition, we just weight people, and we can weight people differently at different times. So we eliminate the time-varying confounding. The disadvantage of weighting is that if there are people in the data who are doing things that are not very common, then they will end up with very high weights, and that will increase the variance and can create some problems with the estimate not being stable. And that has to be dealt with, and there are different ways of doing that too. But it's probably the simplest of the 3G methods to explain. So we typically start there.
Okay, yeah, that's a good point. And I think the last point that you made, that the weights don't need to be stable for an individual patient, but they can vary over time as you have time varying covariates that have an impact on the treatment, like CD4 counts in HIV that determine whether you switch treatment, or maybe in schizophrenia it could be kind of certain symptoms that trigger a treatment switch. These type of things you can take into account to make sure that you compare different treatments or different treatment strategies in the best way. So for the listeners, we talked now about causal inferences, and we talked quite a lot about one of the key things that we need to think about whenever we talk about estimands, that is what is actually the treatment that we are interested in, or what are the treatment strategies that we are interested in. And we talked about the advantages of observational data versus clinical trial data. Even when we use network meta-analysis, we talked about different ways to adjust for these at baseline and also for time varying covariates. And also finally, how to best explain that to someone that is not a statistician, which I think is really, really useful. So for the statisticians, what do you think are kind of your key takeaways that they should have when they go into observational research? And maybe you can also point to some of your favorite resources that you would people recommend.
To me, the most important point is to realize that good study design is good study design, and that it applies both to randomized trials and to observational studies. That anything that we do in a randomized trial and we think is good study design should be done also in an observational study. So if in a randomized trial, we will never compare current users versus never users, or use person time comparisons, anything that we don't do in a randomized trial, it's probably for a good reason. And then we shouldn't do it in an observational study. One example that I like a lot is how in a randomized trial, we always have measures of absolute risk and measures of relative risk. But in many observational analysis, we only see the measures of relative risk. We don't see the measures of absolute risk, just because people have not been taught how to generate adjusted absolute risk, which are not very hard to do. So the message is, if you know how to analyze a randomized trial well, then you know how to analyze an observational study, a follow-up observational study well, and vice versa. And really no fundamental difference in the analysis, with the difference, of course, that in an observational study, we need to adjust for baseline confounders when we are trying to estimate the observational analog of intention to treat effect in a randomized trial. But if we think about estimating the per protocol effect in a randomized trial, or the observational analog of the per protocol effect in an observational study, in both cases, the analysis is exactly the same. And in both cases, we need to adjust for confounders, both at baseline and post-baseline. So if we know how to analyze an observational study with time-varying confounding, then we know how to conduct a per protocol analysis, a non-naive per protocol analysis of a randomized trial with non-random, non-adherence. It's really the same, and we need to do some effort to make sure that statisticians and data analysts can go from one to the other, as opposed to be like, I only do trials and do this, and I only do observational studies and I do this, because that prevents us from understanding better that data analysis for causal inference from follow-up studies is the same, whether the data are randomized or not.
Yeah, that's a very, very good point. As I have worked both in observational studies and clinical trials, I can see there's a lot of benefit of learning from each other. It's quite interesting to see that lots of the research that was done in observational studies about causal inference is now being used in randomized trials with the advent of the estimands and better taking care of understanding what is really the treatment that we're interested in, which I think wasn't very well addressed before we talked about estimands in the clinical trial setting. However, it was a topic for lots of discussion in the observational area long before. That's a really good point. Any specific references you would like the reader to guide to, the listener to guide to?
Well, I like more people to read the causal inference book that I wrote with Jamie Robbins, Causal Inference, What If? You can just Google it and find it. It's free. You can download it from our website. And there we go in much more detail over many of these issues. There's also a number of papers that members of the causal lab that I direct at the Harvard School of Public Health, papers that apply these methods, this way of thinking of observational analysis for causal inference, are really just our attempt to emulate a hypothetical randomized trial, which we call the target trial. So these papers, any of the papers that have been published in the last couple of years, will, I think, can serve as a guide for people who want to learn more about this way of thinking.
Thanks so much. Yeah, and we will share these links in the corresponding blog post. So just head over to the Effective Statistician and search for this episode, and you'll easily find this. Thanks so much, Miguel. It was great talking to you.
Thank you very much.
The show was created in association with PSI, and the PSI conference happens in June in Gothenburg. Head over to psiweb.org. Thanks to Rain and her team, who helps with the show in the background, and thank you for listening. Reach your potential, lead great science, and serve patients. Just be an effective statistician.